how the universe will evolve, what physics predicts about the future. Stand outside on a clear night and look up. Those stars scattered across the darkness, those distant points of light that have watched over humanity since our ancestors first walked upright, they won't be there forever. The universe you're gazing at is not a fixed stage, not an eternal backdrop. And physics, for all its equations and uncertainties, has something profound to tell us about where this cosmic story is heading. We know the universe had a beginning. About 13.8 billion years ago, everything that exists erupted into being in what we call the Big Bang. Space itself began expanding, carrying matter and energy outward in a grand unfolding that continues to this moment. But every story with a beginning raises an inevitable question. How does it end? This isn't idle speculation or philosophical musing, though it touches on both. This is physics real, observational science wrestling with the deepest questions we can ask. What will happen to the stars? What will happen to the galaxies? What will happen to space itself? The answers matter, not because any of us will witness these distant epochs, but because understanding the universe's trajectory changes how we see our place within it. Tonight, we're going on a journey through deep time. We'll explore what modern physics predicts about the universe's fate, examining three major scenarios that scientists have developed based on observations and theoretical understanding. Some of these predictions are strange. Some are unsettling. All of them are humbling. But together, they paint a picture of a cosmos far more dynamic, far more temporary than our everyday experience might suggest. The universe is evolving, right now, beneath the apparent stillness of the night sky. And the direction of that evolution toward cold silence, violent dissolution, or perhaps even rebirth depends on forces and phenomena that science is only beginning to understand. Let's begin by reading the universe's current behavior, by understanding what's happening right now that will determine everything that comes after. Reading the universe's current behavior? For most of human history, we believed the stars were eternal, unchanging, fixed to a celestial sphere that rotated but never transformed. Then, in 1929, Edwin Hubble made an observation that shattered this ancient certainty. He discovered that distant galaxies weren't standing still relative to us. They were moving away, and the farther away a galaxy was, the faster it appeared to be receding. The universe was expanding. This wasn't galaxies flying through space like shrapnel from an explosion. This was space itself stretching, carrying galaxies along with it like raisins in rising bread dough. Between any 2 points in the universe, more space was appearing, moment by moment, pushing everything apart. The implications were staggering. If the universe was expanding now, it must have been smaller in the past. Trace that expansion backward far enough, and you arrive at the Big Bang, a beginning, a moment when all the space and energy of the cosmos emerged from a state of unimaginable density. For decades after Hubble's discovery, cosmologists assumed the expansion must be slowing down. Gravity, after all, pulls everything together. Even if the initial impetus from the Big Bang had set the universe expanding, gravity should be working like a brake, gradually decelerating that expansion. The question wasn't whether the expansion would slow, it was whether it would slow enough to eventually reverse, causing the universe to collapse back in on itself. Then came 1998, and another discovery that rewrote everything we thought we knew. Two teams of astronomers, studying distant supernovae, exploding stars that serve as cosmic measuring sticks, made an observation that defied expectation. These supernovae were dimmer than they should be, which meant they were farther away than predicted. The expansion of the universe was accelerating. This made no sense according to any known physics. Gravity should slow expansion, not accelerate it. Something else had to be at work. Some force or property of space pushing outward, overwhelming gravity's inward pull. Scientists gave this mysterious influence a placeholder name: dark energy. They called it dark, not because it blocks light, but because it remains invisible to all our instruments. We can only detect it through its gravitational effect on the universe's expansion. And despite being invisible, despite being completely mysterious, dark energy appears to dominate the cosmos. Current measurements suggest it makes up approximately 68% of the total energy content of the universe. Regular matter, stars, planets, gas, dust, everything we can see accounts for less than 5%. The rest is dark matter, another mysterious substance we detect only through gravity. So, how do astronomers measure this cosmic expansion and the acceleration that dark energy causes? They use several ingenious methods, each providing a different window into the universe's behavior. The primary tool is something called redshift. When a source of light moves away from us, its wavelengths stretch out, shifting toward the red end of the spectrum. By measuring how much a galaxy's light has been redshifted, astronomers can determine both its distance and how fast it's receding. This technique revealed Hubble's original discovery and continues to map cosmic expansion. Another crucial method involves type Ia supernovae, which serve as what astronomers call standard candles. These stellar explosions occur when white dwarf stars reach a critical mass and detonate with remarkably consistent brightness. By comparing a supernova's observed brightness to its known intrinsic brightness, astronomers can calculate its distance with high precision. These supernovae provided the evidence for accelerating expansion. A third technique examines something called baryon acoustic oscillations. Essentially, sound waves that rippled through the early universe and left their imprint on how galaxies are distributed. These patterns provide a cosmic ruler, a standard distance scale that astronomers can use to measure how the universe has expanded over time. All these methods converge on a picture of a universe expanding ever faster, driven by dark energy. But here's where the story gets even more interesting and more uncertain. In recent years, precision measurements have revealed something troubling called the Hubble tension. Different methods of measuring the expansion rate yield slightly different results. Observations of the early universe, particularly the cosmic microwave background radiation, suggest one expansion rate. Measurements of nearby supernovae suggest a slightly faster rate. This discrepancy isn't huge, but it's statistically significant, and it refuses to go away with better data. Some scientists wonder if this tension hints at something fundamental we're missing, perhaps that dark energy isn't constant, but changes over time or varies across space. And then, in 2024 and 2025, observations from an instrument called the Dark Energy Spectroscopic Instrument, or DESI, began suggesting exactly that. DESI mapped millions of galaxies across 11 billion years of cosmic history, creating the most detailed, three-dimensional map of the universe ever made. The data hinted that dark energy might not be constant after all, but could be evolving, weakening over time. Even more striking was preliminary research published in November 2025 that challenged something even more fundamental. A team of scientists analyzing supernova data suggested that when you correct for certain effects in how these stellar explosions occur, the expansion of the universe may not just be slowing in the far future. It may already be decelerating right now. According to this controversial analysis, dark energy appears to be weakening more rapidly than anyone expected, and the universe may have already transitioned from acceleration to deceleration. This is controversial. Other scientists are scrutinizing the analysis, questioning the corrections applied, testing the conclusions. Science works through this kind of productive disagreement, gradually converging on truth through repeated observation and debate. But the mere possibility that our understanding of cosmic acceleration might need revision shows how much we're still learning about dark energy and the universe's trajectory. What we can say with confidence is this: Dark energy exists, or something very much like it does. It influences how space expands. It began dominating the universe's dynamics approximately 5 billion years ago, when the universe had expanded enough that matter became too diffuse to counteract dark energy's outward push. And whatever dark energy is, whether it's a property of space itself, a new field permeating the cosmos, or something stranger, it will play the decisive role in determining the universe's ultimate fate. Understanding dark energy means understanding whether the universe will expand forever or eventually collapse. Whether expansion will remain gentle or become violently destructive, whether the cosmos will end in ice or fire or something altogether different. With this foundation established, with our understanding of what the universe is doing right now, we can begin to explore the futures that physics predicts. The first scenario we'll examine is perhaps the most widely accepted among cosmologists, though it's also, in its way, the most melancholy. It's called heat death. Heat death. The universe that slowly goes quiet. In the 1,850 seconds, physicists were grappling with a revolutionary set of ideas about energy and heat. They discovered that while energy could be transformed from one form to another, chemical energy to heat, heat to motion, something was always lost in the process. Not energy itself, which was conserved, but the usefulness of that energy. Heat flowed from hot objects to cold ones, never the reverse. Systems naturally move toward equilibrium, toward sameness. This insight crystallized in what we call the second law of thermodynamics. In its simplest form, it states that entropy, a measure of disorder, or more precisely, of unavailable energy, always increases in a closed system. The implications seemed clear, and they deeply disturbed the Victorian scientists who first understood them. If entropy always increases, then the universe itself, the ultimate closed system, must be trending toward a state of maximum entropy, a state where all energy has spread out uniformly, where no differences remain to power any process, where nothing can happen anymore. Lord Kelvin, the physicist William Thomson, called this the heat death of the universe. It was a prophecy written in the laws of thermodynamics. Eventually, the cosmos would run down like a clock winding down, reaching a state of perfect equilibrium from which nothing could disturb it. The name is misleading. Heat death doesn't mean the universe burns up in some final conflagration. It means the opposite. A universe grown cold, dark, and utterly still. A universe where heat energy has become so evenly distributed, so diluted, that it can no longer do anything useful. The end of all process, all change, all complexity. Modern physics has refined this picture considerably, but the basic logic remains sound. If the universe continues expanding forever, as current observations suggest, then heat death appears to be our cosmic destiny. Let's trace this slow dissolution, this incremental surrender to entropy, across the almost incomprehensible timescales it requires. Right now, today, the universe is in what we might call its glory days. Stars shine across the cosmos. Galaxies swirl with billions of suns. New stars are still forming in great clouds of gas and dust. The universe is active, energetic, far from equilibrium. This is the only universe any human has ever known. This era won't last forever. Star formation depends on vast clouds of hydrogen and helium gas collapsing under their own gravity. But as more and more of this gas gets locked up in stars and stellar remnants, less remains available to form new suns. Within 1 to 100 trillion years, the range depends on various factors. Astronomers are still measuring. The universe will exhaust its fuel. After that, the universe will darken gradually as existing stars burn through their remaining fuel. Small stars, the red dwarfs that make up the majority of stellar populations, burn their hydrogen slowly and can shine for many trillions of years. But even these patient suns will eventually consume their nuclear fuel. The last of them will flicker out perhaps 120 trillion years from now. After that, the age of starlight ends. No new photons streaming from fusion reactions. No warmth radiating across space. The universe will contain only the remnants of stars, white dwarfs, neutron stars, and black holes. White dwarfs are the cooling embers of stars like our Sun. Neutron stars are the collapsed cores of more massive stars, objects so dense that a teaspoon of their matter would weigh as much as a mountain on Earth. Black holes are regions where gravity has become so intense that not even light can escape. These objects will dominate the universe for an almost unimaginable span of time, and they will be slowly, inexorably, dying. White dwarfs will radiate away their residual heat, cooling toward the temperature of space itself, eventually becoming black dwarfs' cold, dark spheres of degenerate matter. Neutron stars will follow a similar fate. Even black holes, which seem like the ultimate end state, the final prison from which nothing escapes, will eventually evaporate. This is where quantum physics enters the story. In the mid-1970s, Stephen Hawking discovered that black holes aren't perfectly black. Quantum effects at the event horizon cause them to emit radiation now called Hawking radiation and very slowly lose mass. The smaller a black hole becomes, the faster it radiates. Eventually, any black hole will completely evaporate in a final burst of energy. But the timescales involved beggar imagination. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, containing millions or billions of solar masses, would persist far longer. One with a billion solar masses wouldn't evaporate for approximately 10 to the power of 100 years. That's a 1 followed by 100 zeros. Written out. 10,000 million 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 years. During this inconceivable stretch of time, matter itself may be decaying. Some theories suggest that protons, which make up atomic nuclei and appear stable over timescales we can measure, might spontaneously decay given enough time. If this happens, the predicted timescale is at least 10 to the power of 40 years, though estimates vary widely depending on the theoretical model, ranging from 10 to the power of 31 to 10 to the power of 41 years or longer. Every atom and every remnant structure would eventually disintegrate, leaving only electrons, positrons, photons, and neutrinos. Throughout all this, the universe continues expanding, driven by dark energy. Objects that were once neighbors in a galaxy find themselves separated by distances that increase without limit. Eventually, the observable universe from any given point will shrink to nothing but the immediate local region. Everything else will have receded beyond the cosmic horizon, moving away faster than light can travel through the intervening space. What remains after all this, after the last black hole evaporates, after matter decays, after every possible process has run its course, is a universe containing only extremely dilute radiation and isolated particles. These particles are so far apart that they rarely, if ever, interact. This is heat death. Not a moment of dramatic ending, but a gradual fading into cold, dark quietness. In this state, entropy has reached its maximum. Energy is spread so uniformly that no gradients exist to power any process. No stars can form, no chemistry can occur, no life can exist. Time itself becomes meaningless in a sense, because time is measured by change, and nothing changes anymore in a system at maximum entropy. The universe has reached thermodynamic equilibrium. The German physicist Rudolf Clausius, who helped develop thermodynamics, wrote in 1865 that the entropy of the universe tends to a maximum. If he was right, If the second law applies universally, then heat death seems inevitable for an eternally expanding universe. But is it? Some physicists have questioned whether we can truly apply thermodynamics, developed for closed systems in laboratories, to the universe as a whole. The expanding universe isn't a closed system in the usual sense, it's constantly creating new space. Some have suggested that in an expanding universe, the maximum possible entropy increases faster than actual entropy, meaning the universe continually moves further from equilibrium rather than approaching it. Others point out that we don't fully understand quantum gravity, and that our extrapolations over such vast timescales assume current physics remains valid. Perhaps new physics emerges at extreme scales of time and space. Perhaps quantum fluctuations eventually create new pockets of low entropy, new beginnings within the dying cosmos. These are speculations, attempts to find loopholes in what seems like an inexorable conclusion. For now, based on what we understand about physics and what we observe about the universe, heat death remains the most likely outcome if expansion continues forever. It's a strangely peaceful ending in its way. Not violent or catastrophic, but gentle, quiet, gradual. The universe doesn't shatter or burn. It simply runs down, like a clock unwinding, until stillness prevails. All the drama, all the structure, all the complexity that emerged over billions of years, stars and galaxies, planets and life, slowly dissolves back into simplicity. But there are other possibilities. Other ways the universe might end that are far more dramatic, far more violent. One of them, called the Big Rip, involves dark energy not remaining constant but growing stronger, eventually tearing apart not just galaxies and stars, but atoms, space, and time itself. The Big Rip. When expansion overcomes everything. Dark energy, as we've discussed, drives the accelerating expansion of the universe. In the standard model of cosmology, this dark energy is treated as a cosmological constant, a fixed property of space that remains unchanged as the universe evolves. Every cubic meter of space contains the same amount of dark energy, and as the universe expands and creates more space, the total dark energy increases, but its density stays constant. This cosmological constant is characterized by something called the equation of state parameter, usually written as the letter W. For ordinary matter, W equals 0. For radiation, W equals 1/3. For the cosmological constant, W equals -1. That negative value is what gives dark energy its peculiar repulsive character, its ability to drive space apart. But what if W isn't exactly -1? What if it's slightly less than -1? This might seem like a technical detail, a minor variation in a parameter, but the consequences would be catastrophic. If W is even slightly less than -1, dark energy isn't a constant at all. It's something else. Something that gets stronger as the universe expands. Physicists call this phantom energy, and it would lead to an end of the universe so violent, so total, that it dwarfs every other scenario we've discussed. To understand why, we need to grasp what makes phantom energy so strange. Normal matter and energy become less dense as the universe expands. Imagine a cubic meter of space containing a certain number of particles. As the universe expands, that cubic meter becomes larger, but the number of particles stays the same, so the density decreases. Even radiation works this way. As space stretches, the wavelength of light increases and its energy decreases. Dark energy as a cosmological constant behaves differently. Its density remains fixed even as space expands. You could think of it as a property of space itself. So more space means more total dark energy, keeping the density constant. Phantom energy would be stranger still. Its density would increase as the universe expands. The more space there is, the more phantom energy per unit volume. It's as if space itself possesses a kind of springiness, and the more you stretch it, the harder it pushes back. Or imagine holding a stack of banknotes between your hands. If phantom energy were real, pulling your hands apart would magically create more money between them, continuously, increasingly. This creates a runaway feedback loop. Phantom energy drives expansion. Expansion creates more space. More space means more phantom energy. More phantom energy accelerates expansion further. The cycle amplifies itself, faster and faster, until it reaches a singular moment of infinite expansion in finite time. That moment is called the Big Rip. The mathematician and cosmologist Robert Caldwell and his colleagues first seriously explored this scenario in 2003. They calculated what would happen if dark energy has an equation of state parameter W less than -1. The results were dramatic and specific. Let's walk through a hypothetical timeline, using their example of W equal to -1.5 to see how a big rip would unfold. We start today, 13.8 billion years after the Big Bang. The phantom energy is subtle, its effects barely distinguishable from a cosmological constant. But as the universe expands, its influence grows. For billions of years, the cosmos seems relatively normal. Galaxies still exist, stars still shine, but the accelerating expansion gradually strengthens. The space between galaxy clusters grows faster and faster. Galaxies that were once neighbors find themselves racing apart at ever-increasing speeds. Approximately 200 million years before the Big Rip, galaxy clusters begin to unbind. The space between galaxies expands so rapidly that the gravity holding clusters together can no longer resist. Galaxies drift apart, isolated, each becoming an island in an ever-expanding void. About 60 million years before the end, individual galaxies start to disintegrate. The space within galaxies expands faster than gravity can maintain cohesion. Stars that orbit the galactic center together for billions of years suddenly find themselves unable to complete their orbits. The Milky Way, if it still existed, would come apart, its billions of stars scattering as the fabric of space between them stretches beyond the point where gravity can hold them together. 3 months before the Big Rip, planetary systems dissolve. The space between a star and its planets expands so rapidly that gravitational bonds snap. Earth would separate from the Sun, drifting off into interstellar space as that space itself grows. But the Sun and Earth wouldn't drift intact for long. In the final minutes, stars and planets are torn apart. The phantom energy, now incredibly strong, overwhelms the electromagnetic forces holding solid matter together. Rocky planets shatter. Stars explode. Every celestial body dissolves into its constituent atoms as space itself pulls everything apart. In the last fraction of a second before the end, atoms themselves disintegrate. Electrons are ripped from their nuclei. Then, in the final 10 to the power of -19 seconds, a tiny fraction of time, far shorter than anything we can directly measure, even atomic nuclei come apart. Protons and neutrons dissolve into quarks. And then, at the moment of the Big Rip itself, space tears completely. Not just everything in space, but space itself reaches a singularity of infinite expansion. What happens beyond this point is genuinely unknown. The equations break down. General relativity, which describes space and time, becomes meaningless at infinite curvature. Perhaps space fractures into disconnected regions. Perhaps a new physics takes over. Perhaps the concept of beyond has no meaning because time itself has ended. This is the Big Rip, the most dramatic, most total ending physics can currently envision for the universe. But how likely is it? Current measurements of W, the equation of state parameter, place it very close to -1, consistent with a cosmological constant. Most analyses find values like -1.03, plus or minus some uncertainty. Given the measurement errors, W could be exactly -1, in which case there's no big rip. Or it could be -1.000001, barely distinguishable from -1, in which case a big rip would occur but trillions upon trillions of years in the future. The problem is fundamental. We can never measure anything with perfect precision. There will always be some uncertainty, some error bars. This means we can never say with absolute certainty that W is exactly -1, rather than, say, -1.00000001. And if it's even that slightly less than -1, phantom energy exists, and a big rip will eventually occur. Some physicists take comfort in the fact that even if phantom energy exists, the big rip would be pushed so far into the future. Estimates range from 200 billion to 10 to the power of 100 billion years or more, that all the structures in the universe would have decayed anyway. Heat death would effectively happen first, and the big rip would just be the final punctuation mark on an already dead cosmos. Others note that phantom energy itself violates some expectations of physics. It requires negative kinetic energy, something that doesn't normally occur in nature. It would be, in some sense, a ball that naturally rolls uphill. Most theoretical physicists are skeptical that nature allows phantom energy, but they can't definitively rule it out. And there's something oddly appropriate about the big rip as a thought experiment, even if it never occurs. It forces us to confront the idea that the universe itself is temporary. Not just stars and galaxies, not just life and consciousness, but the very fabric of reality might have an expiration date. Space and time themselves might not be eternal. The Big Rip represents the most extreme form of impermanence physics has seriously considered. But it's not the only alternative to eternal expansion and heat death. There's another possibility, older and in some ways more hopeful, that imagines the universe not ending at all, but renewing itself. This is the idea of collapse, of a big crunch, and of cycles that might repeat forever. Big crunch and cyclic ideas. Collapse, rebirth, or endless return. In 1922, the Russian mathematician Alexander Friedmann derived solutions to Einstein's equations of general relativity that described how the universe could evolve over time. One of his solutions showed that if the universe contained enough matter, its expansion could eventually slow, stop, and reverse. Gravity would win its long battle against expansion. The universe would begin contracting. This contraction would be, in many ways, expansion played in reverse. Galaxies that had been moving apart would start approaching each other. The cosmic microwave background radiation, cooled to just a few degrees above absolute zero by billions of years of expansion, would begin to warm as its wavelengths compressed. Space would shrink. As contraction continued, galaxies would begin to merge. Stars would start colliding with increasing frequency. The universe would become denser, hotter, more compressed. Eventually, everything would collapse back toward a singularity, a point of infinite density and infinite temperature. This cosmic apocalypse became known as the Big Crunch. In the decades after Friedmann's work, the Big Crunch seemed like a real possibility. Whether it would occur depended on the density of matter in the universe. Above a critical density, gravity would eventually overcome expansion and pull everything back together. Below that density, expansion would continue forever. Throughout much of the 20th century, cosmologists worked to measure the universe's density and determine which fate awaited us. Then came 1998, and the discovery that expansion is accelerating, driven by dark energy. This observation seemed to rule out the Big Crunch. With dark energy pushing space apart ever faster, gravity appeared to have lost its battle. The universe would expand forever, approaching heat death not collapse. But the recent observations we discussed earlier, the hints that dark energy might be evolving, weakening over time, and particularly the preliminary November 2025 study suggesting expansion may already be decelerating, have reopened questions cosmologists thought were settled. If dark energy is indeed weakening, if acceleration has already given way to deceleration, then the possibility of eventual contraction returns. The Big Crunch might not be off the table after all. Even if a simple Big Crunch seems unlikely given current evidence, the idea has evolved into more sophisticated forms. These cyclic models of the universe suggest not just one episode of expansion and contraction, but an infinite series of cycles, each perhaps billions of years long, with the universe endlessly dying and being reborn. The appeal of cyclic models is deep and ancient. The idea that the universe repeats itself appears in Hindu cosmology, with its concept of endless cycles called kalpas. The ancient Stoic philosophers proposed ekpyrosis, a periodic conflagration where the universe would be consumed by fire and then renewed. Even Einstein, in 1931, briefly considered cyclic models before abandoning them. The problem that killed early cyclic theories was entropy. As Richard Tolman showed in 1934, if the universe goes through cycles of expansion and contraction, entropy must increase with each cycle according to the second law of thermodynamics. This means each cycle would be longer and contain more disorder than the last. The cyclic model didn't eliminate the need for an initial state. Modern cyclic models attempt to solve this entropy problem through various mechanisms. Let's examine the most prominent ones. One approach comes from string theory and involves extra dimensions beyond the familiar three of space and one of time. In this picture, our entire universe, everything we can see, exists on a sort of membrane, or brain in the jargon, floating in a higher dimensional space. There might be other brains nearby, separated by tiny distances in these extra dimensions. In 2001, physicists Paul Steinhardt and Neil Turok proposed the ekpyrotic model, in which two such brains periodically collide. Each collision generates tremendous energy, which, from our perspective, looks like a Big Bang. The universe expands for billions of years, then begins a slow contraction. But instead of collapsing to a singularity, the brains bounce off each other, triggering another expansion. This cycle repeats endlessly. The key insight is that each cycle involves net expansion. The universe grows slightly larger with each iteration. This increasing volume allows entropy to increase without building up indefinitely, avoiding Tolman's problem. The universe never resets to exactly the same state. Each cycle is slightly different, slightly larger, carrying forward some but not all of the information from previous cycles. This model remains speculative. String theory itself, while mathematically elegant, lacks experimental confirmation. The dynamics of colliding brains are not fully understood, but the ekpyrotic approach shows how modern theoretical physics might accommodate cyclic cosmologies that earlier generations thought impossible. A quite different cyclic model comes from the Nobel laureate Roger Penrose, whose conformal cyclic cosmology takes a radically different approach to the question of cosmic renewal. Penrose begins with the observation that the late universe, if it experiences heat death, will be in a very particular state. Those black holes will have evaporated through Hawking radiation. What remains is nothing but photons, massless particles of light, and perhaps other forms of radiation spread throughout an exponentially expanding space. Here's Penrose's key insight. In such a universe, nothing has any mass. And without mass, there's no natural way to define size or duration. A universe filled only with massless particles is conformally equivalent to an infinitely small point. You can mathematically transform one into the other by rescaling distances and times. This allows Penrose to perform an extraordinary trick. The end of one universe, its far future, at heat death, can be mathematically matched to the beginning of another universe, its Big Bang singularity. The infinite future of one aeon, as Penrose calls each cycle, becomes the beginning of the next. Time doesn't stop. It continues smoothly from one cycle to the next. The universe doesn't crunch and bounce. It expands forever within each aeon, but that infinite expansion somehow transforms into the next Big Bang. This is deeply counterintuitive. How can an infinite future become a singular beginning? The answer lies in the mathematics of conformal transformations and the physics of massless particles. Without mass to provide a scale, the vast, cold, ancient universe of the far future is physically identical to the hot, dense, tiny universe just after the Big Bang. They're the same state, viewed from different perspectives. Penrose has suggested we might find evidence for this theory in the cosmic microwave background radiation. Collisions between supermassive black holes in a previous eon might leave imprints, concentric circles of slightly different temperature that we could detect in today's CMB. Searches for these circles have been conducted, with controversial and inconclusive results. Most cosmologists remain skeptical, but Penrose's model has the virtue of making testable predictions. Yet another approach to cyclic cosmology comes from loop quantum gravity, a still theoretical attempt to quantize general relativity at the smallest scales. In this framework, space and time themselves are made of discrete quantum units. When the universe contracts toward what would classically be a big crunch singularity, quantum effects become important at incredibly high densities. These quantum effects provide a sort of pressure, a bounce, preventing the universe from collapsing to a true singularity and instead causing it to rebound into a new phase of expansion. This quantum bounce would be a real, physical process governed by the equations of loop quantum gravity. Unlike Penrose's conformal matching, which is more of a mathematical identification, the loop quantum cosmology bounce involves matter and energy passing through a bottleneck and emerging into a new, expanding universe. The state before the bounce influences the state after it, providing a kind of information transfer between cycles. What all these modern cyclic models share is an attempt to avoid the problems that plagued earlier versions. They incorporate dark energy in various ways. They address the entropy problem through increasing volume, information transfer, or quantum resets. They make contact, at least in principle, with fundamental theories of quantum gravity and high-energy physics. But they also remain highly speculative. We have no direct evidence that the universe has ever undergone such a cycle before. We can't yet test most predictions of string theory or loop quantum gravity. The mathematics is sophisticated, but the connection to observational cosmology remains tenuous. And yet, the appeal endures. There's something deeply attractive about a universe that renews itself, that doesn't end but transforms. Perhaps this appeal is psychological, reflecting our human discomfort with finality, or perhaps it reflects an intuition that the universe, having created time and space and matter once, might do so again. The recent evidence that dark energy might be weakening adds a new wrinkle to these considerations. If expansion is indeed slowing, if it might eventually reverse, then some form of collapse becomes physically possible, even without exotic physics or extra dimensions. Whether such a collapse would lead to a true big crunch, a quantum bounce, or some other outcome remains unknown. But the question has moved from the realm of pure speculation back towards something physics might eventually answer through observation. What would it mean if the universe were cyclic? How would that change our understanding of our place within it? Before we can address these questions, we need to zoom out even further to consider what any of these cosmic scenarios, heat death, big rip, or cyclic renewal means for us, here and now, in this brief moment of cosmic time. what it means for us. The human perspective. Let's return to Earth for a moment. Let's return to human scale, to the timeframes that make sense to beings who measure their lives in decades and their civilizations in millennia. Written history extends back perhaps 5,000 years. Agriculture emerged 10,000 years ago. Anatomically, modern humans have existed for roughly 300,000 years. Homo sapiens and our close relatives have walked the Earth for a few million years. The Earth itself formed about 4.5 billion years ago. The universe began 13.8 billion years ago. Now consider the timescales we've been discussing for cosmic endings. The last stars won't die for 120 trillion years. Black holes will evaporate over spans measured in 10 to the power of 100 years. These numbers are so large, they cease to mean anything in human terms. There's no way to intuitively grasp the difference between 1 trillion and 10 to the power of 100. Both are, in practical terms, forever. This vast gulf between human timescales and cosmic timescales shapes how we should think about the universe's fate. First, and most obviously, we will never witness any of these endings. Humanity will be long gone. Life on Earth will be long gone. The Earth itself will be gone, consumed when the sun expands into a red giant approximately 5 to 7 billion years from now. The sun will die as a white dwarf perhaps 5 billion years after that. All of this happens in what amounts to the opening moments of the cosmic story, long before any of the scenarios we've discussed even begin to unfold. We live, in cosmic terms, at the very beginning of time. The universe is young. Stars are still being born in profusion. Galaxies are still colliding and merging, creating spectacular new structures. The universe is energetic, active, dynamic. We inhabit the era of light and complexity, and this era will persist for timeframes that dwarf the entire history of life on Earth many times over. This perspective can be humbling, but it shouldn't be diminishing. Yes, we are tiny compared to the cosmos. Yes, our existence occupies an infinitesimal fraction of cosmic time. But there's another way to see it. The universe, for all its vastness, is apparently very good at being empty and dead. Space is mostly vacuum. Most atoms don't form molecules. Most molecules don't form cells. Most star systems don't produce life. Intelligence appears to be vanishingly rare. We've found no evidence of it anywhere but here. The universe spends most of its volume and most of its time being nothing but void and radiation. But right here, right now, on this small world orbiting an ordinary star, the universe has become aware of itself. Matter has organized itself into structures capable of consciousness, of thought, of wonder. The atoms that formed in stellar furnaces billions of years ago have arranged themselves into patterns that can contemplate the Big Bang, calculate the universe's expansion, predict its eventual fate. This seems unlikely in the extreme. The fact that it happened at all is remarkable. Perhaps we are common, and the universe teems with intelligence we simply haven't detected yet. Perhaps we are rare, a fluky accident in an otherwise barren cosmos. There's a concept in Buddhist philosophy called anicca, which is usually translated as impermanence. It's one of the 3 fundamental characteristics of existence in Buddhist thought. Everything that arises must eventually cease. All phenomena are temporary. Nothing lasts forever. This teaching isn't meant to inspire despair, but rather to encourage a certain kind of awareness, a way of being present with things as they are without clinging to them or demanding they remain unchanged. The impermanence of things is not a flaw in the universe, but simply how the universe is. Modern physics and cosmology can be seen as arriving through very different means at a similar understanding. And it will, in one way or another, end. Stars will cease to shine. Galaxies will disperse or collapse. Even atoms and space itself may not last forever. Does this render everything meaningless? Does knowing that the universe will eventually reach some form of ending, whether cold silence, violent dissolution, or mysterious renewal, negate the significance of our existence? Many philosophers have grappled with this question. Some argue that meaning requires permanence, that if everything is ultimately temporary, then nothing truly matters. Others counter that meaning is context-dependent, that the eventual heat death of the universe, trillions of years hence, has no bearing on whether your actions and relationships matter right now, in your life, in your community, in your historical moment. The physicist Alan Lightman has written eloquently about what he calls the temporary universe. He notes that we long for permanence in a cosmos that offers none. We want our lives to matter eternally, but we live in a universe where even stars have lifespans. This can feel like a cosmic injustice, a fundamental mismatch between our desires and the nature of reality. But Lightman also suggests that impermanence gives significance to the present moment. If stars shine forever, any particular moment of starlight means less. Because they don't. Because every star will eventually die. Each moment of light is precious. The fact that our existence is temporary doesn't diminish its value. It concentrates that value into the actual moments we have. Consider, would you rather experience something beautiful that lasts forever, but means nothing, or something beautiful that's fleeting but profound? The question reveals how we intuitively understand that meaning isn't just a function of duration. A moment can matter intensely, even if it doesn't last. The universe gave us eyes to see the stars, even though those stars won't always exist. It gave us minds to understand entropy and expansion, even though understanding doesn't change the outcome. It gave us hearts capable of love and grief and wonder, even though every individual consciousness eventually ceases. Perhaps this is enough. Perhaps it has to be. There's also something inherently beautiful in our uncertainty about the universe's ultimate fate. Despite all our observations, all our theoretical work, we still don't know for certain which scenario will unfold. Dark energy remains mysterious. The equations of quantum gravity remain unsolved. New observations continue to surprise us, like the recent hints that dark energy might be evolving in ways we didn't predict. This uncertainty isn't a failure of science, but a reflection of how science actually works. We build models based on observations. We test predictions. We refine our understanding. But we remain humble about what we don't know. And the universe seems endlessly capable of presenting us with phenomena we didn't anticipate. Future observations will help. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will create detailed three-dimensional maps of dark energy's effects across cosmic history. The European Space Agency's Euclid mission is already gathering data on how dark energy influences the universe's expansion over billions of years. These and other instruments will provide the most precise measurements yet of how the universe is evolving. Perhaps they'll confirm that dark energy is a true cosmological constant, pointing toward heat death. Perhaps they'll find evidence that it's evolving in ways consistent with phantom energy, raising the specter of the Big Rip. Perhaps they'll reveal something entirely unexpected, some new physics that changes our whole framework for thinking about cosmic fate. This openness to surprise, this acknowledgement that we might be wrong about fundamental things, is itself a kind of wisdom. The universe has surprised us before. The discovery of expansion surprised Einstein, who had assumed the cosmos was static. The discovery of acceleration surprised cosmologists, who expected deceleration. Each surprise taught us something profound about reality. There may be more surprises waiting, more revisions to our understanding, more moments when observation forces theory to adapt. This is the excitement of living in a time when we can ask these questions and have hope of answering them, even if the answers raise new questions in turn. So, what does it mean for us, personally, existentially, that the universe will someday end? Perhaps it means that we're participating in something larger than ourselves, something that includes all of cosmic history, the formation of atoms in the early universe, the birth of stars from clouds of gas, the emergence of planets and life and consciousness. We're a chapter in that story, a brief but vivid chapter, full of its own beauty and meaning. Perhaps it means that this moment right now, with stars shining in a dark sky, with consciousness aware of the cosmos, is precious precisely because it's temporary. This is the universe's bright age, its era of complexity and light, and we're fortunate to be here to witness it. Perhaps it means that the search for meaning should be local rather than cosmic. What matters is how we treat each other, how we engage with the mystery of existence while we can, how we contribute to the ongoing experiment of consciousness and culture during our brief time on stage. The universe will end someday, but that day is unimaginably distant. Between now and then stretches a span of time so vast that all of human history so far amounts to less than an eye blink. We have no shortage of time on the cosmic scale. What we have a shortage of is time on the human scale, the individual lifetimes, the generations, the centuries of recorded history. This is where our focus belongs. Not on a heat death trillions of years hence, but on the heat of living existence right now. Not on the hypothetical big rip of space itself. Not on whether the universe will eventually collapse or cycle, but on how we can build lives and societies that honor the improbable gift of awareness in a vast and ancient cosmos. The universe's ending, whatever form it takes, is written in the laws of physics. But those same laws also allowed for stars and planets, for chemistry and biology, for nervous systems and brains and the emergence of creatures who can look up at the night sky and understand what they're seeing. That understanding, that moment of connection between a conscious mind and the cosmos it inhabits, is its own kind of miracle. But while it lasts, we've traveled far tonight, across timescales that strain comprehension and through scenarios that range from quiet fade to violent rupture to eternal return. The universe's future, as physics currently understands it, could follow any of several paths, each strange in its own way. Heat death remains the most widely accepted scenario among cosmologists. If dark energy continues to drive expansion as it has for the past 5 billion years, the universe will expand forever, gradually cooling and dissipating until all usable energy has spread uniformly across space. This won't happen quickly. The last stars will shine for trillions of years, black holes will persist for unimaginably longer, but eventually, entropy reaches its maximum, and nothing further can occur. The Big Rip, while less likely given current measurements, represents the most dramatic alternative. If dark energy proves to be phantom energy, growing stronger as the universe expands, then acceleration could become so extreme that it tears apart galaxies, stars, planets, atoms, and eventually space itself in a final moment of cosmic dissolution. Cyclic models offer a third possibility that the universe doesn't end but renews itself through processes we're only beginning to imagine. Whether through bouncing cosmologies derived from quantum gravity, through Penrose's conformal matching of distant future to new beginning, or through brain collisions in extra dimensions, these models suggest that death might not be the final word, that the cosmos might recreate itself again and again. And hovering over all these scenarios is our current uncertainty. Recent observations suggesting that dark energy might be evolving, that expansion might already be decelerating. What we think we know today might need revision tomorrow as new data challenges old assumptions. But beneath the differences, these scenarios share something profound. They all acknowledge that the universe is not eternal in its current state. Change is fundamental. Impermanence is written into the laws of physics as deeply as conservation of energy or the speed of light. The cosmos that exists today, bright with stars, structured in galaxies, hospitable to complexity, is a phase, not a permanent condition. This shouldn't diminish our wonder. If anything, it should enhance it. We exist in the universe's spring, its era of exuberant creativity. Stars are still being born by the billions. Galaxies collide and merge, spawning new generations of suns and planets. The cosmic microwave background, that ancient light from the Big Bang, still bathes everything in its gentle glow. A reminder of where we came from. This is the bright age of the cosmos, and it will last for timescales so long that the entirety of human history, every empire that has risen and fallen, every story told, every work of art created, all of it, amounts to less than a moment. We're not witnessing the universe's twilight. We're witnessing its dawn. And somehow, incredibly, some small portion of the matter in this universe has organized itself into structures capable of understanding this. We can look at the night sky and see not just points of light but distant suns. We can measure the redshift of galaxies and deduce that space itself is expanding. We can trace that expansion backward to a beginning and forward to possible endings. We can write equations that describe the behavior of reality at scales unimaginably large and small. The universe has become aware of itself. That awareness is temporary. Individual consciousnesses arise and cease. Civilizations likely do the same, but while it exists, it represents something extraordinary. Matter contemplating matter. The cosmos examining itself. Existence puzzling over existence. This is our privilege and our responsibility. To witness, to understand, to care. The stars you see tonight won't shine forever. The galaxy we inhabit will one day be torn apart by expansion, or dissolved in collapse, or transformed in ways we can't yet imagine. But right now, in this moment, they exist. They're real, and we're here to see them. That seems like enough. If you found something meaningful in this exploration, if the journey through cosmic futures resonated with you, I'd be grateful if you'd consider liking this video. Subscribing to the channel helps me create more of these deep dives into the mysteries the universe presents. Your support makes it possible to keep exploring these profound questions together. But more than that, I hope you'll take a moment tonight, or tomorrow night, or whenever the sky is clear, to simply look up, not thinking about heat death, or the Big Rip, or cyclic cosmologies. Just looking, seeing, being present with the vast and ancient cosmos that somehow produced you, that gave you eyes to see it and a mind to wonder about it. The universe is evolving. It has a past and a future. And for this brief, precious moment, we're part of that evolution, conscious participants in a cosmic story whose ending we can glimpse but not witness. Make peace with that. Find wonder in it, and keep looking up. The stars are still there. For now, that's enough.